Hi there and welcome back to Tripplikit and to part 5 of the synthesizer tutorial. And this time we will actually finally get to build a working oscillator. So without further ado, let's get going. First though, we need to be able to convert pitch to frequency. This is because musically we work in terms of pitch, specifically MIDI note, whereas our oscillator is controlled by frequency. Basically, for one octave, pitch goes up 12 semitones, while frequency doubles. So, we know that for concert A, the MIDI note number is 69 and the frequency is 440 Hz. This allows us to write this equation. Now, we don't want to be calculating powers every sample, as this takes up a lot of processor time, so we need a more efficient method. However, our processor is very efficient at multiplying and dividing by factors of 2 using left and right shift instructions. This means that we only need to convert pitch to frequency for one octave and can shift this result an appropriate amount to get the values for all the other octaves. Before we can look at how we convert from pitch to frequency, we need to consider how we're going to represent pitch and frequency, as MIDI note number and Hertz are not the most convenient for our purposes. Let's consider pitch first. For efficiency, we're going to convert pitch to frequency using a lookup table. To make that easy, we're going to store our pitch values in this 32-bit format. The top 16 bits give the octave, though this will only actually ever go up to 10 or so. Our table will be 256 entries long, and we will use interpolation again to achieve the accuracy we want. So bits 8 to 15 give the position within the lookup table, and bits 0 to 7 give the interpolation value. And to frequency. Actually, we want to maintain a 32-bit wave phase value. Here we can see the phase value relative to our sawtooth wave. Every sample we increment this wave phase value, and this phase increment value is what controls the frequency. Say for instance we increment the phase value by 4000000. Now from now on I'm just going to say 40, just give the first 2 digits, otherwise it gets a bit tedious. In successive values, the phase will be 00, 40, 80, C0, and then it'll wrap round back to 00. Thus the wave will repeat every 4 samples, so this, in our case, will give a frequency of 12 kHz. And you can see that halving this phase increment value to 20000000 halves the output frequency again. As we will see later, we can convert this phase value to a position in a wavetable simply by right shifting it. Okay, let's see how this works in practice. Okay, so here is the oscillator code. Let's just quickly go through it. First thing we do, we take the oscillator pitch, which we've calculated previously. Again, this is note plus pitch bend plus any modulation. And we put it in a union called an MG pitch union. Okay, here's this union. We just have all 2 words and 4 bytes. That enables us to basically use the 32-bit number and get the 2 16-bit words and the 4 8-bit bytes out of it without having to do a lot of shifting. So we get our MG pitch union, and from that we extract a table index and a table interpolation, as we saw previously. So now we calculate the phase increment. Here we are just going to calculate the phase increment for the top octave. So we have 100 minus the interpolation value and the interpolation value, and the pitch to frequency table, the values are such that when we multiply them by 100 in hex we get a full 32-bit value. And here we just take the phase increment and we shift it down for the pitch octave, which is this value, and of course the higher the octave, the bigger the phase increment, so we shift it down by a constant minus the octave. We get down here, and the oscillator phase we simply add the phase increment to for this sample. This function is called every sample. And then we get the waveform for the current oscillator phase. And this is the function that gets the waveform. Again, the scale 32 union is just a 32-bit value and two 16-bit values, so we can extract them without having to shift. Okay, so we have here a table phase, which is the table offset plus the interpolation value, and to get that we shift right the phase value by the wavetable shift, which we generated when we generated the table. So now this table phase fits inside the table. So the wavetable position is the most significant word of the table phase. So we get the value low is the low value from the table. We increment the position to get to move on to the next value called the high value, and we mask into the table in case we've gone beyond the end of the table. The high value, we then get the high value here, and moving down here we get an interpolate value from the least significant word of the table phase, and we interpolate between the wavetable value high and wavetable val low into our out val, and then we simply return our out val to the oscillator do function, and then for now we simply return that to the voice do function, and the voice do function simply for now sends that out to the output, and it's written to the WAV file. Okay, so we've got some code. Does it work? Well, here we have a little sequence file that will just generate each note in turn, starting at MIDI note 0 and finishing up away down here at MIDI note 127. So, shall we see what that does? And this is just diagnostic stuff. And it's done. Okay. So let us load up trusty cool edit program. That's that one. Looks promising. Let's see what it sounds like. Okay, that seems to be working. Let's have a look at the spectral view, and there we go. We can see at low frequencies, because our maximum table size is 1024, that's the maximum number of harmonics we can get in it. And thereafter, yes, as our tables get bigger, we're adjusting the number of harmonics, so the maximum harmonics is around the same frequency, right up to here, where we're using the smallest table and we're saying we're beyond the range of the instrument. So we don't care about aliasing. Okay, so now we have the same thing, except every note as it plays, the pitch bend goes up 1 octave. So if we've got it right, the maximum harmonic should end somewhere up near the Nyquist frequency. So should we give that one a go? There she goes. Run, we go back into here and we load that one. Shall we listen to that again? Not terribly exciting, but again, let's look at the spectral view. So there we go. That seems to be fine right till we get up to high frequencies. We get all sorts of aliasing, but we know about that. And let's have a look more detail at that. Yep, that seems to be working just fine. Okay, so we've got a sawtooth wave, but a conventional synthesizer oscillator also has a square stroke pulse wave capable of pulse width modulation. So how are we going to go about generating that? We don't really want to generate a load more tables for square wave, and anyway, if we did that we couldn't do PWM with it. So this is how we're going to do it. Okay, it's nice to have the time to go into things in a little more detail, and to demonstrate how this works I wrote this little PC program. So shall we fire this up? Okay, so here it is. So here is our sawtooth wave, which we've generated already. Now let's take a second sawtooth, and this sawtooth we can adjust the amplitude from full plus to full minus, and we can adjust the phase from in phase to completely out of phase. Okay, so let's set the amplitude to 100% negative, -1, and let's set the phase to 50%. And let's add these together. And lo and behold, the result is a square wave. And what's even more clever is if we change the phase of this second wave, we get square to pulse, we get pulse width modulation. And we can continuously vary the wave between square and ramp, which a conventional oscillator you can't do, it's a switch. And if we set them to positive, we can vary the result waveform from here, which is basically the sawtooth, to here, which is a sawtooth wave of twice the frequency. So we get a free oscillator effect, if you like. So shall we look at how we implement this? Okay, so here we are. This is what we had before. The out valve is our sawtooth wave, and now we have a second wave phase, wave 2 phase, and this is the original oscillator phase plus wave 2 phase difference, and that for the same wave shape always remains constant. It's just an offset, and we can add that on, and that is what we use to vary the spacing between the waves and the pulse width. So we have a wave 2 val, which is actually a scale 32 for reasons we'll see, and we now get the sawtooth wave for that from the OS2 wave phase, using the same function as we did for the original sawtooth wave, and we multiply that by wave 2 amplitude, which is plus 100% to minus 100%, as we saw in the little demo, and we add the most significant word of that, because if we multiply 16 bits by 16 bits we get 32 bits, and that's our out val. So that's it. Those 4 little lines we've added gives us all those features we saw on the little demo program. So shall we run that? That was quite quick, and that's done. So shall we go into good old cool edit and load it in, and there we go. It's one note all the time, no pitch bend, so we can see it's not doing anything nasty and generating any aliasing or unpleasant harmonics. So we'll go back and look at the waveforms. Shall we play it? Okay, let's have a bit of a closer look what's going on in here. So this one is morphing between a sawtooth wave and a square wave over the note length. So you can see it goes along, and I'm just scrolling through the image of the waveform here, getting more and more like a square wave, and a square wave at the end. So the next one, come on, is demonstrates pulse width modulation. So it starts as a square wave, and you see the negative going part is getting thinner and thinner, and there we go, that's down to a pulse, and that's the end of it. And this one is demonstrating the sawtooth wave to sawtooth wave twice the frequency effect I described. And we have this intermediate wave, and it comes through, and at the end we have a sawtooth wave of twice the frequency. So shall we hear those again? So finally we have a fully working oscillator. We will be revisiting the oscillator because there are some oscillator features yet to be added, but for now that'll do. Now it's a lot easier and a lot more pleasant working on a synthesizer if you can actually make some kind of fairly musical noise rather than just beeps. So I'm going to try and sort of add features in an order that makes it easier to do that, to make musical sort of sounds out of it, to test it. So next up we're actually going to look at the envelope, which should be a lot more straightforward than the oscillator. So then at least our oscillator beeping noises will have their amplitude shaped in a musical fashion. So I think until then it's goodbye. So if you like the channel, please subscribe, leave a comment. If you've got anything to say, thumbs up would be nice. If you have any questions on the content of this video, don't hesitate to ask. I'll leave my email in the description, and I'll leave links to where you can download zips of all the code I've developed for this video. So for now it's goodbye from Tripplikit, home of interesting electronics. Goodbye.